Hello and welcome back to Calculus 1, section 3.2 on derivative as a function. The last time we defined the derivative as a function which generates all of the slopes of tangent line. We also said that we can obtain it using that limit formula. So we can quickly push through one of these calculations and say find the derivative of f of x equals, I don't know, let's just do x squared plus 1, whatever. So looking for the derivative of that. Now we said that the derivative will be given by the limit h goes to 0, and then we have the difference quotient. That will be f of x plus h minus f of x divided by h. And from this formula we see that we need to make this piece, and we can get that by plugging the values in. So I don't want blue. So I want limit h goes to 0. Make this a little bit longer. And say now instead of x I have to put x plus h squared plus 1. So that would be this. Then we have minus the original function, which is x squared plus 1, everything divided by h. So that's where we start. We go into limit h goes to 0, and then we have now, we expand, so that's x squared plus 2xh plus h squared plus 1 minus x squared minus 1 when you distribute. And now we cancel x squared and minus x squared, positive 1 and negative 1, which leaves us with the terms that have h. You can factor h and get 2x plus h over h. This is where h cancels. And we have limit h goes to 0 of 2x plus h. When h goes to 0, the answer is just 2x. So we learn, or we discovered, that if the function is equal to, let's say, x squared plus 1, the derivative of the function is the function 2x. And the procedure to find this derivative was purely taking the limit from chapter 2. We did not learn yet how to take derivatives without limits. So this entire procedure was something that it's fair game for the exam, because problem like this you are going to find in the homework for 3.2. Sorry, for 2.3. So the entire calculation here, if I just scratch this off, the entire thing you see on a page currently is just a basic 2.3 calculation. You are just finding the limit using the algebra method that we said you have to use when you have denominator equals 0. And then last class, we added the meaning to that calculation you learned earlier. And we said that that function that you get at the end is going to be called the derivative. And that function will generate those slopes of tangent lines. So gives m tangents. There we go. Gives m tangents. So now we have this as like a pair. Function and its derivative. And if you look at this carefully, you see that they're both functions. I can graph these two on the same coordinate system. Now I'm going to change this one into red, let's say. And now let's go and, no, red. Okay, good. And now let's graph them to see that they both fit, right? So we have the x squared plus 1, that's a parabola. It's going to be lifted 1 unit, so that's 1. And the other one has a slope of 2, so it's going to do this. Oh, that's red. So the other one is a line like that. So this is my f prime, and this is f. So for the entire lecture today, because that's what we are doing today, we're graphing function and the derivative to learn the way they work together. I will always use black for the original function f of x, and I will use red for the derivative. So that's the color coding for today's class. So if I draw both of these on the coordinate system over here, we immediately see, I mean, both of these are functions. They both pass what we call the vertical line test, right, where you draw these vertical lines, and the vertical line is allowed to cut through the function only once. If it cuts more than once, then it means it's not a function, right? The curve is not a function. We have circle, and we have ellipse, and we have sideways parabola, we have hyperbola. Like, all of these are not functions because, you know, once you draw vertical line test at any point, right, it cuts twice. So if you are able to find a location for something like this, also your inverse sine and cosine, unless you here in inverse cosine, right, would do this forever unless you restrict the domain, right? That one would fail infinitely many times on the vertical line test. So none of those are functions because vertical line test fails. But in our case, right, over here, vertical line test would pass everywhere, and both of these are functions. And this lecture is about learning the how are they connected. So there is one thing that we immediately see from this. Well, there are two things actually. One is the increase decrease, and then the other one is the minimum of a function. But I'm going to split the minimum to another example. So I'm just going to keep here with, let's say, 1 and 2. So number 1, when f of x is increasing, f prime of x is positive. That's it. Positive. There we go. And number 2, when f of x is decreasing, f prime of x is negative. Now, since we read from left to right, we will be observing this way, right? So if you are walking down this slope, right, because you are going to the right, you will be going down the slope. That means that the function is decreasing. And if the function is decreasing, you see that all of the derivative values here, all of these derivative values right here, they're all negative. All of the y values are negative values for that part of the derivative function. On the other side, as you climb up the mountain over here, this is hard work, so you have this and maybe a rope. I don't know why that rope is around your neck, but whatever. You're going up. Maybe you should remove the rope. Let's make that into an arrow. How about that? So you're going up the slope, that means that the function is increasing, and increasing function, as you can see, it has all of the positive values of the derivative. So now we are learning this connection between the function and the derivative, where if function is increasing, derivative is positive. If the function is decreasing, derivative is negative. This is going to hold for all functions and their derivative pairs. All of them, including the ones you haven't learned. For instance, you haven't learned hyperbolic functions yet. You will learn those in Calculus 2. Hyperbolic functions will still follow this rule. So, any of the, thousands of functions out there, and what you've probably seen about 20 to 25 at most, right? There are thousands of functions out there. This relationship here fits all of them. Every function in existence has this as a rule. All right, the next part. The next example is going to be what I promised earlier with the minimum and maximum and how those show up in the derivative, right, in terms of the graph. So what I'm going to do is I'm going to do somewhat a problem which was there, which you might have on a homework, something very, very similar. And then we're going to analyze that further. So I'm going to draw something like this and say what the homework says, draw the derivative. I'm not giving you this function, right? So on the exam, your calculator, graphing calculator, websites to cheat and all of that stuff, it's all useless, right? Because this black line is not given, and if you don't know and don't understand the concept, you do not get to do the problem, right? And most of the exams and stuff will be like that, obviously, because it will be high in concept and not as much with the computation and things, because, right, situation. But look at this. If I want to draw this, I know that the maximum point right here and the minimum point right here are places where increase turns into a decrease and then decrease turns into increase. Those are very special points. Now, what we learned up there in blue is that the increase and decrease, right, they get to be, the derivatives get to be positive or negative. So what is in between positive and negative? What is in between positive numbers and negative numbers?
0.
0, beautiful, right? So if we know that for this part of the line here, derivative must be positive because it's going up, and on the other side has to be negative because it's going down, we know that at this maximum we have to have a 0. And the same thing will go for minimum. The derivative will go through x-axis for every minimum and maximum. Now you can also understand that through this, if you studied your tangent lines, you see that you have the horizontal tangent line. And what is the slope of the horizontal line?
M equals X.
No, horizontal line. Y equals X is a 45-degree line. That's Y equal X, and the slope is 1. Now, how about the horizontal line? What's the slope of the horizontal line?
0.
0, perfect. Slope is 0 on the horizontal line because it's not sloped. It's flat, right? So there is no slope to the horizontal line. Slope is 0. So when you put a round object on a horizontal surface, because it's not sloped, it's not going to roll in any particular direction. It is just going to stay there. So slope is 0. For both of these, we call them horizontal tangencies. And we know that this is actually the value of the derivative, which is why it's 0 when you look. So this is just another way to look at the situation of why when you have min and max, why do you get 0 for the derivative? And now you can quickly just, draw the line through this. You have to have positive line over here to the left because derivative is increasing. You have to have a positive line as well on this side because the derivative is the function is increasing. So increasing function means positive derivative, meaning derivative should be above x-axis. And now to connect this with a negative, well, that's easy. And we are getting some kind of a parabola. Those of you who paid attention in pre-calculus, you know that your ax cubed functions plus bx squared plus cx plus d, you know that they graph this way. And then those of you who know that ax squared plus bx plus c are parabolas and they graph like this, we see that if you do that limit, you do the limit procedure, you will see that the derivative of x cubed is x squared. But again, do you know that by looking at graphs? Right? Do you know that using the pre-calculus knowledge from before? So now we have f and f prime. And remember, I don't know equations here. I don't know any of the equations. So now we discovered the third point, and that third point says that f prime equals 0 at every min-max of f of x. So that's another rule, and it's very easy to now graph these functions even if you don't know what they actually are, to use a graphing utility. It's very easy to go back and forth between the two. And one more point. So last class, I also said, what if f of x is equal to 1 over x? And then over here you do the limit procedure, and it will spit out f prime of x is equal to negative 1 over x squared. So now, if you graph this, we're again going to use black for original function and red for the derivative. The original function is 1 over x. Remember, we're going to draw this function 5,000 times. The derivative function in red, when you graph it, it looks like this. And that's f prime. Do we have everything match previous points, right? 1, 2, and 3? The answer is yes. First of all, point 3 is irrelevant because we do not have minimum or maximum for the function f of x equal 1 over x. So 1 over x does not have what we call extreme points, extrema. f1 over x does not have min and max. Since it doesn't have min and max, you see that your red line never crosses x-axis, because min and max are the two points that would create 0 for the derivative, which is actually where the derivative crosses the x-axis. Now we had two of those before. We had min and a max, and you can see that the red line cuts through the x-axis twice. So every min and every max creates another 0 for line from the derivative line to go through. But in this case, we did not have any min and max in our problem. And as you can see, the derivative, which is the red line, does not cross x-axis because there are no zeros. Now, are the rules 1 and 2 satisfied? Well, yeah, right? If you look at the black line, both of those pieces are decreasing pieces, and both of those pieces should give negative values for the derivative, for the red line. So increase or decrease of the original function gives us the positive or negative on the derivative. And you can read that backwards as well, right? If you, because on exam, you run into, here is a random function, draw the derivative, here is a random derivative, draw the function, right? And as I said, calculators and graphic utility, everything is useless because you do not have a function, right? You just have some stuff, and we'll see what those look like. Now, we have determined that all 3 points that we talked about so far fit here. But then there is one more, the new one, the number 4. I hope you see that the vertical asymptote location is preserved. So f of x and f prime of x will have the same vertical asymptote. You know what? Asymptote, possibly multiple asymptotes. So vertical asymptote location is preserved from function to its derivative. And that carries through all of these, right? Through any function that you have. We are going to learn eventually, to reinforce this a little bit, we are going to learn eventually that if the function is ln x, the derivative of that function will be 1 over x. Now, if you draw both of these functions, you draw ln x, and you see that there is a vertical asymptote where the y-axis is. And if you draw 1 over x, you still have the same location for the vertical asymptote. So vertical asymptote is preserved. Now, we are not talking about ln yet, so I'm going to erase this. I just wanted to give you another example of this situation where if you have a vertical asymptote for the function, you have the vertical asymptote exactly at the same place for its derivative. So these are the 4 things that we need to know for us to be able to sketch the graph of the derivative looking at the function, or sketch the graph of the function looking at the derivative. There is also one more thing that I am going to mention now, and that is, what if your function is constant? So f of x equals constant. C. What do you think the derivative would be in this case? Does anyone remember what the derivative measures from last class? We said it gives the slopes of the tangent line, great, but I said at the beginning and somewhere towards the end, I know I said at least twice. Derivative measures
Instantaneous change.
Beautiful. It measures change, yes. instantaneous change, but for my particular question right now, change is enough. And what is a change in constant? Just note the absurdness of my question. What is the change of a constant?
The slope.
0.
0. It's called constant, right? Because there is no change in it. Something is constant and it's just no change. So the derivative would be 0. So if I am to draw this, so this is my x-axis, this is my y-axis, and let's say right here is c. So this is my y equals c, the function. My derivative is just going to be this 0 along the x-axis. Now, does this make sense? Well, is there increase or decrease? No. So derivative is not allowed to be positive or negative. And how about min and max? Well, every point is a min and max, right? Because there are no higher, there are no lower points. So all of these points along the straight line, all of them are minimum and maximum at the same time. So just all fall onto 0, 0, 0, 0, 0, 0, 0. Every single one of them, right? Because if you take a look at what maximum means, right? If you have a maximum here, it's higher than all of the points, right? On left and right of that. And the minimum the same way. Minimum is the lowest point to all of the points to the left and to the right. So when you have a straight line like this, then every single point along that line is minimum and maximum at the same time, right? So if the function is constant, then derivative is just this flat line at 0. And the reason is derivative measures change, and there is no change in a constant. Therefore, right, you're not going to get any line going up or down or anything like that. You're just going to have, well, this red line across. So what type of a question do you expect on homework and an exam and so on? Well, it simply says, sketch the derivative given, and then you just have this graph. Now the graph, is going to be like this. We'll place a vertical asymptote somewhere, like this. And then I'm going to go like this, stop, go like that, stop, go flat, stop, and then go down, follow the asymptote. Then let's say come out of the asymptote from the other side and just go up forever like this. This is your f of x. This is going to be something that is called a piecewise function. You can take a look at the first piece and call it a parabola, like negative x squared, shifted up, down, left, right to match the curve. Then you have the linear piece over here, y equal mx plus b. Then you have a constant piece over here. And then this piece over here, we said, could be negative 1 over x squared, if you remember the graph from before. And then you just shift it up, right, to go through the asymptote, because remember, it used to be like this, right? The x-axis was its asymptote on top. And now it's just shifted up. And you do that just by simply adding a value of some kind to the end. So I have these functions, but I don't care what they are. I mean, I could pick up the points along the way, and do the curve fit, right? Do the curve fit, and it would work great. And also here I can pick up the points and calculate, and I see that the constant is 2, right? So it's not a big deal. We can do that. But we don't have to. The beauty of this derivative is that if you know those 4 rules, you know immediately how to draw entire derivative, because derivative shows the change, the slopes of the original function. So you would say, oh, I have an increasing function up to this point, and this point over here, yeah, that point is a maximum. So if I have increasing function, I better have some kind of a positive derivative there. And then I have a decreasing function. But if you take a look at this piece, this function decreases at the constant rate, which means this is going to be some kind of a derivative like this, which is a negative value. We can actually, take a look at these points and compute what that value is. Should be -3 actually when I look at it better. -3. Because your slope over here is 3 units up. 3 units down and 1 unit forward. It's actually 1.5 units forward. I had it right the first time. Well, it doesn't matter. Whatever. So that's that piece. Then we have a piece where it's constant. And that's going to be the 0 derivative, because there is no change there. And then I have a decreasing function. I have to follow the asymptote. And now on this side is increasing function, which means the derivative needs to be positive. If I am to delete this black line, the only thing that stays on the graph would be the f prime. The entire red line is f prime. And now I'm going to analyze this line to see. If I look at the first, we are ignoring everything else. It's gone, right? There's nothing there, nothing to see. We are only looking at the first part up to the first point where the function changes into a different function. We see increasing function, and increasing function means that you are going to have positive derivative, which is why we draw the curve above x-axis. Now, we also see that there is a rapid change here. This is hard to climb right here, right? Steep. It's hard to climb. And you can see that the derivative on that part of the line shows this rapid change, right? It's a rapid change because it curves quickly up. And then you get to this part here that it's easy to climb, and you see how the derivative calmed down, right? It's not as sloped. This part here is also easy to walk. So the slower the increase or a decrease of the function, the less angled is the derivative. So that's the first part. We see that we have, that's how we know it's a curved line, by the way, because it's changing how hard it is to climb up this particular slope. Now we go to part 2. Part 2 is right here. And again, the rest of the graph doesn't exist. This, what you see here in between these two highlight pink lines or whatever, that's the piece of the function that you can just have as a separate function, and the derivative will still be the same. So we see a constant drop. So there is a constant change, and it's the constant change in the negative because you are losing the value. And that was also number 2 rule that we had today, which said that if your function is decreasing, the derivative is negative. And we also see that we are supposed to put a flat piece because the linear equation there, which is whatever y equal mx plus b you get. So that linear equation will have a slope, and its slope will be this value we got, -3 or whatever. So that's that part. Then we have the part which I already explained. I don't think I can add anything on it. Constant is not changing, therefore its derivative must be 0. So you just ride the x-axis on that one. And finally, we get to the part where we get to introduce our rule 4. Vertical asymptote has to stay at the same location. You cannot change the location of the vertical asymptote. The derivative will change the function from original function into the derivative of that function. In some sense, think about it that the derivative operates on functions and changes functions just as functions would change numbers. But we'll talk more about that later in the course. So, for this last piece, what do I have? I have a decreasing function, that's the black, and then I also have a red that is going down. Red is going down to the left of the vertical asymptote because the function is decreasing. Now, on the other side, when you look at the black line, it's increasing, which is why our derivative, which is red, is above x-axis and it's positive. So now I'm going to make up one more of these, like a little practice, and then sketch the derivative. And I'm going to give you some time to try and figure it out and go back to rules and the other example to draw. So I'll give you some couple of minutes, and then you guys, then I'm going to do, and you guys are going to see what I have. So here it is. So we're going to start with, let's go a drop like this, and then falls back into the origin. And now at the origin, it's going to jump over here. I should have had that open circle. There we go. Go across, stop, go up, stop, and then let's say go pew, like this. Forever and forever. So draw this is your f of x. Draw the derivative on your own. Let's see. All right, this would be more than enough time. This is more than enough time to draw the function. We have to pick up immediately on min and max, put those as zeros, so we always start there. So here is the minimum, that's going to be a 0. Here is a max, that's going to be a 0. And we also pick up immediately on the constant part, which has no change. That has to be a piece right here that is a 0 piece. So these two, picking up min and max values and putting 0 for each one of them, and then getting the constant pieces out, is something that we immediately put down. And then we can start connecting. For instance, what are the easy parts, right? Well, easy part over here is to see, right? Just the way I drew this line at 45 degrees, we know that slope is equal to 1. It's a constant slope for the whole thing. So here we go, right? That's a constant piece. It's at 1 because the slope of that line is 1. So no change here, slope is 0, and then we are moving into a constant change of 1, so the value of that is 1. And then we have this decrease part. Now decrease part means it is negative on the derivative, so we can go to this point where the 0 is and just draw the piece that is going down. So we completed the whole right side quickly, and that's our f prime. Now on the left side, I have two pieces. I have a piece that is decreasing and a piece that is increasing. Decreasing piece has to have a negative derivative, and the increasing piece has to have a positive derivative. Now, positive derivative, meaning it's going to be above, and now you can ask yourselves, is it going to go bend down, right? Or is it just going to go up and stop? Well, analyze what you have for this little piece of the line. I hope you see the horizontal tangency here. That means that the slope is 0. That slope was inching little by little by little by little to get up to somewhere here where the slope is m equals to 1. And then that slope starts still rising and rising and rising and rising. So I am inclined, right, to put this to be some kind of line like this, because this graph doesn't bend back into a 0 slope. Let me give you that example on a larger picture here. So if this little piece did this, right? If it created this slope, you see it starts here as a slope of 0, and over here technically creates a maximum, so it creates another horizontal tangency of m equals 0. This slope would look like that, because it starts with a slope of value 0. It is a really high value slope in the middle, and then ends being a slope of the value 0. Now, a lot of people are confused that, increase and decrease is read as numbers for the red line. But once you understand that there are these, not millions, but infinitely many little tangent lines at every single point that you can possibly think of, and then each one of these points gives us a value m equals a number, then when you say for x equals, I don't know, -3, you have a slope of 0 that literally becomes -3, 0 to draw. And then let's say over here at -2, your slope was, I don't know, 7. Then the point there, this point, becomes -2, 7, because the slope of the tangent line had the slope of 7. And once you pick up all of the x values and the slopes of those are creating the y values, you are able to plot point by point and then have the function. But see, there was this requirement here for the line to go into here with this curve that flattened and created horizontal tangency m equals 0, which is why it bent back into 0. I don't have that here. I don't have it. It is going straight in, and it's going straight in at the slope of, let's say, -1. So I could have just said, boom. Sorry, slope of +1. This is positive lines are like this, and the negative lines are like that. So there was a positive slope of 1, and here's 1, let's say. So it's just going to be this piece. It's not going to bend back because this curve went like this rather than like that. It's a very subtle change, and for people that are sloppy with their graphs and don't care and are not analyzing and learning this, it's not going to go well, right? You really have to understand how different these two lines are. And even in your mind, if you say, well, I'm not an artist, that doesn't matter, right? What matters is that the line on the right is the one that goes back to the 0 slope, which would produce this type of the derivative function, and the other one over there produces this type of the derivative function. So those little pieces, those little subtleties, right, are the things that you have to study, and you will be better, right, as time goes on, the more problems you do. So obviously, if you're just doing the bare minimum and you need way more than the bare minimum, clearly it's not going to go well. But sketch the derivative is one of the standard problems. You see the function, and then you're able to sketch the derivative function because the black line does give you all the change that you need to see. Places where there is no change, places with a positive change, which is constant, another place where the positive change, but it's not constant, the decrease, which is the negative change, and you can see that for both of those that I circled, your red line is below x-axis because the derivative values are all negative on them. And that pretty much sums it up. You are able to draw the function looking at the derivative, and you are able to draw the derivative looking at the function. Now, let's say derivative is given and you want to sketch the function. Sketch the function given the derivative. And now let's say I give you the derivative that looks like this. So this is your f prime of x. Does anyone recognize this graph?
It's a cosine graph.
Beautiful. It's a cosine graph. I'm not telling you that, right? I'm just like, okay, fine. So what do we know? Well, we know from the rule 3 that anytime the derivative goes through 0, original function has min and max. there are no asymptotes, so rule 4 is out. But for the rule 3, there is this line. This is not an asymptote, this is just a construction line. And then there is another line right here. And those lines have either a min or a max on them. Now, if you haven't thought about these things, you can draw min and max on the side and understand that in order to have a min, you have to have a decrease followed by increase. And to have a max, you have to have an increase followed by decrease. Because this increase-decrease changes as you go through min and max. So the reason why this is a minimum is because the function was decreasing, 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 and then hit the minimum, and then it bounces up. Where this one was increasing, hits the maximum, right? And then goes down, right? Hitting the ceiling. You can just go down. Can't go through the ceiling, right? So, what situation do I have? We know that the positive over here spells the increase, and the negative value spells the decrease, and the positive value spells the increase again. So now, increase turning to decrease, increase to decrease is a max. So I'm going to have some kind of max. It doesn't have to be in line, right? It doesn't have to be in line with this. So I have some kind of max right there. And then the other one will have some kind of minimum. And now I don't need these lines anymore. Now, what else do I know? Well, I see that I have a min and max, and I know that I need to connect these two with a line like this, because this is a decrease here. And then I have to show increase on this side, and I have to show increase on this side. So now, what is the black line? Come on, what's the black line? It's obvious.
Then
F of x?
It's the sine graph.
It's a sine graph, exactly. So now, just by this visual over here, you learned the 3.5 topic, that if you have the derivative to be cosine x, then the original function was sine x. And we didn't even compute any of that stuff. We didn't see that as a formula yet. We didn't do anything with it, right? We didn't do the limit on it. We have done nothing. We just looked at the graph and we found out that the derivative of sine is cosine. These are very powerful things, these graphs and these rules. If you sit down, analyze, and right, but this is not one of those when you heard the lecture and then you said, well, exam is not coming up for this, so and homework is not due until next Thursday, so you only learn this if you actually sit down and think about these things a lot and try them as soon as possible so you don't forget these rules. Now they will come back later in the course, these things, and usually where these things show later are higher level courses in engineering, because a lot of engineering professors don't want to be bothered by doing mathematics and calculating. They just draw the graph and they pick the values or trends or whatever they need off of that graph without actually computing and doing things. So graphing will be very important, which is why A lot of four-year schools and universities, Rutgers and GIT included, do not allow any kind of a calculator. So we do not allow graphing calculator on exams. They don't allow any kind of calculator ever for anything. So you are forced to learn these rules because obviously later. Now, you know, why would we care? We don't have a 300 and 400 level courses, right? So we kind of limited to graphing, but they do care because they really need you to be able to go through these things efficiently and quickly. So we found out that last class, we found out that derivative is a function as well. And today we learned those 4 rules that connect functions to derivatives and derivatives to functions. And then you go and you can make the sketch of what they look like as you go one way or the other. The homework for this is already available on my MATLAB. And remember, minimum five questions and all that kind of stuff. I am going to switch the turn off the stream, and we'll be back in about 5 to 10 minutes. I have to also swap the cooling, and I have to put the titles and all that stuff. So 5 to 10 minutes, we'll be back with 3.3 rules of derivatives, and then we'll be done with the day. So we'll be back latest 4:20, but possibly sooner than that. I will see you all soon.